Hello and welcome everybody to this latest Oasys webinar. This particular one, I'm pleased to say, is looking at the Oasys Project of the Year 2014 and the structural finalists. And we've got some rather interesting case studies to look at today. I'm going to start with the academic entries first of all. And this particular one is from Harriet Stone. Harriet Stone is currently studying for an engineering doctorate at the University College London, UCL. She got a civil degree from the University of Exeter and a Masters with distinction from the University of Surrey, which is my old university. And she's looking at seismic vulnerability of structures in Montserrat in the West Indies. So, I mean, earthquakes. It's commonly known that with earthquakes, it's not the earthquake itself that causes disaster, it's the failure of the structures that leads to loss of life and livelihoods and so on. Now, there are countless structures located in areas of high seismic hazard, and many are unable to withstand the earthquake loadings. Now, while engineers can assess the seismic capacity of buildings and recommend strengthening regimes and so on, there are a lot of underdeveloped countries where they just can't afford the services, the work, the time, etc. and so on. Now, in Montserrat in 1905, they didn't have an earthquake, they had a volcano which rendered 2/3 of the island uninhabitable, including most of the major towns, and the remaining population now lives crammed into the top part of the island. But where they're safe from the volcano, even if they're not safe from earthquakes. Over the last 50 years in Montserrat, the construction materials have gradually changed from unreinforced masonry to reinforced concrete. Now, there have not been any major earthquakes since RC frames became the standard construction, which means very few structures have been tested with such ground movements. This, coupled with the lack of building regulations in the country, means that the island's seismic vulnerability is at best unknown and at worst is very vulnerable. Now, Harriet's study concentrated on a recently constructed primary school and emergency shelter in the village of Lookout, and she used a combination of linear and non-linear analyses, and her intention was to compare the two techniques and see if linear analysis could be suitable for detecting structural deficiencies in the island structures. The school she chose is a reinforced concrete frame with solid slabs and non-structural concrete blockwork infill. The blockwork was not modelled, mostly because it was very poorly constructed. There's a 4-inch gap between the two halves of the building, separating into there's a gap between the two halves of the building, separating them into two separate frames, and which means Harriet could model just this one half of the structure. She chose GSA to perform the linear analyses on the frame and another program, the non-linear. And as there are no local or applicable international codes, she used Eurocode 8 and used the French National Annexes data for the nearby island of Guadeloupe. The linear response of the structure was captured under increasing lateral loads, calculating using the base shear values from increasing the ground acceleration from 0 meters per second up to 5 meters per second. The bending moments and forces were then extracted for each element type and compared with the envelope values of the capacity of sections at the yield. She calculated these yield capacities using Oasys ADSEC, which is our reinforced concrete cross-section program. When we look at the ground shaking values, that's and the GSA cracked sections, you can calculate the yield capacity of each element, or the yield capacities with different failure modes. And also there are a number of assumptions built into this process. So she ended up with envelopes of absolute minimum and maximum values, maximum value capacities for each of the sections, and then plotted them on the graph here. As you can see, all the elements are actually failing under the required design loads in both flexure and shear. And in fact, some elements are already at yield under straight gravity loads. So this building, it seems, is barely standing up anyway. Never mind if there's an earthquake. Harriet's conclusion was that linear analysis has a great potential for teasing out the fundamental structural issues during structural assessment of the buildings on the island, and that the more complex and resource-intensive non-linear analysis might not be always the most effective option. She suggests that buildings might be assessed using the more simple elastic methods, and then when important issues are identified, that's the time when you then bring in the more complex analysis. The study also revealed substantial shortcomings in this school building, and the relevant government authorities have been informed. I hope it might be safe for future generations of children. Thank you, Harriet. The next is from Richard Lang of University of Bradford, who has been researching fibre reinforced polymer composite grid shells as part of his MSc. Grid shells are attractive and innovative structures consisting of a double curved lattice of structural elements, and they've proved very well suited to lightweight and large span roofs. The design of grid shells is carried out using a technique known as form finding, where the ideal geometry is determined based on factors such as the structure's loading, the initial geometry, materials, support conditions. In the past, this process involved creating a scale model known as a hanging chain model and taking painstaking series of measurements off it to determine the geometry. This hanging chain model is heavy and flexible enough to form a pure tension shape under gravity. This form can then be inverted and give you the ideal shape for a compression-only shell. Now, whilst this method is very effective, it's also very time-consuming and unfortunately inaccurate. So these days it's been replaced by computer form finding using programs such as GSA Suite, which gives them far more streamlined and efficient process. Richard found that many of the drawbacks of steel and timber grid shells have the potential of being overcome using FRPs, that is, fibre reinforced polymers. He feels it's likely that FRPs have the advantages of both materials, while sharing few of the disadvantages. In order to investigate this, Richard's project consisted of initial research to determine the precise methods and identify constraints on grid shells, a short case study on the existing grid shell. He then used GSA to create and verify a model based on the existing grid shell. He was then confident in using GSA to design several examples of different geometries and configurations against differing loading conditions, and then also laboratory experiments to investigate the long-term effects of creep on FRP samples. As I mentioned, he modelled a number of grid shell configurations, so we will just look in particular at this one, which is his enclosed street. This structure, like the others, was initially form found and then subjected to a variety of load combinations as detailed in the Eurocodes. Wind loads are calculated using an idealized dome and then assigning the resulting pressures coefficients to the different segments of the structure. He found that under ULS loads the structures all behaved well, but under SLS loads, so serviceability limit state loads, he found that the lower lattice modulus of many of the FRPs, which can be a bonus during the form finding and erection process, became a potential problem when checking the serviceability limit states of the structure. Their high flexibility of the material gave rise to some quite large deflections. And he feels this might be overcome by making the grid shell a multi-layered one. Richard's conclusion was that not only might FRPs be used for grid shells, but their properties, in particular the high strength and lower lattice modulus, may make them a preferred material for future grid shells. But under condition that these long-term potential problems such as creep can be overcome. And now we come to the winning entry in the academic category, the retractable roof design at Stadium de Kuip by students Ruud van Knippenberg and Simon Cox. Ruud and Simon are both studying on the Structural Design Master's course at the Eindhoven University of Technology. The Kuip is an existing stadium built in Rotterdam in 1936, and as you might imagine, it no longer meets modern requirements. The brief was thus to design a new roof over the existing stadium that's both retractable and covers the extended stadium with its capacity of 63,000 spectators. The existing Kuip is famous for its smooth and elegant design, so the new roof was designed to be a lightweight cable net and tensegrity structure rather than the large heavy structure. The unique aspect of this design is that unlike most closable stadia, the roof is closed by a sliding membrane from the outside to the middle. This roof is also divided up into 6 segments, giving the appearance of an iris when closed. The final design consists of a slightly oval permanent roof with a closable inner section, as you can see there in blue. The structure of the permanent part of the roof consists of a lightweight pre-stressed cable structure with 2 inner tension rings held apart by struts. The inner roof then uses these 2 tension rings as compression rings to reduce its tension, and the inner retractable roof is constructed out of 6 radial pre-stressed cables, which are curved due to the secondary cables which fan out and onto the primaries. We'll see those a little bit clearer in a minute. Due to the time limit on the study, it was felt best to restrict the analysis down to the following locations: wind overpressure, wind under pressure, and snow load. For serviceability, it was determined that the structure should not deflect more than span of 100 times the system length, and no cable should be able to go flat. Slack, not flat. Right. As you can see, diagrams there, the 2 parts of the roof, the permanent structure in the top left, and the variable, the closable structure in the bottom left, and they then work together to form the complete structure. In their analysis, they broke the structure down into a number of stages. So the first part, they looked at just one set of inner cables, and including the secondary cables, which then set the shape of the main one. The model found there was no relaxation under the governing load cases, with the largest deflections occurring under wind pressure, and again, even under suction, the pretension was sufficient to avoid slack cables. These cables were then combined together to form the complete closable roof, and analysed again to ensure that the design was still acceptable. It's found that due to the increase in the system length, the pre-stress needed increasing to meet the deflection requirements. And the final mode, the compression ring and permanent structure, was also included. It was found that due to the compression of the steel ring, the cable net deflects significantly more, and a maximum deformation in the ring is established. Because the cables transfer the loads to the ring in localized places, the compression ring also has to withstand quite significant bending moments. To alleviate this, additional radial cables for the closing roof were considered. In conclusion, the proposed new roof for the Kuip station is designed by Oasys GSA by the iterative process of form finding and pre-stressing static loads and adjustments, and the end result is a beautiful, lightweight, and indeed moving roof. And the Kuip with Ruud and Simon was a worthy winner, we feel, of the Structural Academic Prize. Well done to you both. Now onto the commercial section. The runner-up was RFR and their team Yui Hu and Florian Rochereau, both in the Shanghai office, and their design of the new Disneyland pedestrian bridge in Shanghai. The RFR team have been working on the double footbridge at the new Shanghai Disney World theme park, which is due to open in 2015. The bridge consists of two decks, one 6 meters wide for pedestrians and cyclists, and the second 3 meter wide glass decked for pedestrians only. This double bridge will be first of its kind in China and unique in the world, considering its scale, which is 120 meters of developed length for an equivalent 9 meter deck width. RFR determined to use GSA for its form finding and vibration capacities, and they're currently undergoing erection studies at the moment. Now, the form finding is pretty complex for a bridge such as this, so to facilitate that multi-stage form finding required, they use GSA's COM interface to initialize the model, but also then to drive the form finding from an Excel spreadsheet. So, stage 1 of the form finding calculates the vertical forces that each hanger needs to take, and at this stage the hanger locations are just pinned in place. These node loads are then carried on to stage 2. So in stage 2 the program sets pre-stress loads in the edge suspension cables and the backstay cables in order to reach the minimum target radial and tangential displacement for the tops of the masts. The third step then adjusts the hanger's pre-stress in order to achieve a minimum geometric deviation from the nominal coordinates. That means when the bridge is under load, it deflects back to the right place, back to level. The routine adjusts the hanger pre-stress until the deck is back in the correct location. Now, as the inclination of the hangers affects the form of suspension cables, steps 2 and 3 are then repeated a number of times until the team was happy. The fourth and final step is to combine all the pre-stress loads found in the previous steps into one complete model, but also for fine-tuning the hanger orientations and for final testing. In the plan on the right, the hangers are all radial with the bridge, but during the form finding, these tended to they need some adjustment to actually achieve that effect, and so quite a lot of cycles round the form finding. Now, combining GSA with Excel and macros enabled RFR to reveal an ideal geometry of inherent force equilibrium between the mast, suspension and hangers. After form finding, RFR then used GSA to investigate the potential for footfall-induced vibration in the bridge. The dynamic studies enabled clear decisions on how to deal with the potential vibration problems. They were able to slim up the deck box section without compromising human comfort, and also add additional mass and or dampers where appropriate. RFR's use of the advanced features for the GSA analysis and links with Excel using the COM interface have enabled them to master the complexity of the form finding for such an excellent suspension bridge. The results are currently being further tested on a 1/75th physical scale model of the bridge. Okay. And finally we come to the winning commercial entry, a spectacular 30-meter high tower designed by Christopher van der Pluge of ABT Engineers in conjunction with the architect Broek Beekema. The main purpose of the tower is branding of the region and also communication of events via the 2 large LED screens. The main structure is a 3-dimensional truss built up of circular hollow sections. The whole is then fabric coated, covered. tower was designed parametrically using a few simple rules. Now, although the tower looks complex, it's actually made up of triangles on plan, each of which rotates relative to each other in such a way that you can bend each primary column on a single plane, thus making fabrication a lot easier. The parametric model was set up in ABT's own software, though Excel and Grasshopper were initially considered. You can see there are a number of parameters, all of which need satisfying for the design. This program then ran GSA directly from this console. Of course, close collaboration with the architect was required to ensure that the geometry was optimized for a slender appearance while still maintaining things like internal space for the staircase. As the structure is large but slender, it's prone to wind loading, so a very careful study was required with optimization and routines for calculating the wind load on each face. Following this, the steel design was then optimized. Wind load governed quite a lot, and along with the hollow steel section connections. These connections needed to avoid things like high peak stresses, avoiding within the CHS connections, uncertainty of behavior, the complex comprehensive geometry, and limited differences between the ULS and SLS loads. The structure's top half, buckling effects and aesthetic constraints tended to govern, whilst at the bottom it was wind-induced fatigue that dominated the design. Calculation of the hollow section connections can be time-consuming, so ABT atomized the design, taking the results directly from the GSA analysis into the spreadsheet. The final model was then exported from GSA into Revit for documentation and communication, and also into technical structures for fabrication. Regarding GSA and the Comlink, the lad Chris had this to say: a structural sound design has been created that was optimized within the available means of the engineering process. The ability to automatically perform large numbers of calculations improved the economic feasibility of the design. This approach has enabled the construction of a new and innovative structure. I'd like to agree with that and say, well done, Chris, a worthy winner for your design. We are hoping to get all these case studies written up and published directly on our case studies section of the webinar, of the website. And I hope you agree that they're impressive structures, and we hope that's inspired you, and we look forward to seeing everyone's entries for next year. The bar has been set quite high. I look forward to seeing how everyone rises to the challenge. Thank you very much.